Physics 30. So today we are going to continue on with, not even today, it's just the next lesson, next part of this lesson. Talk about beta positive decay and how they react, or how they're slightly different than beta negative, like I said in the previous one. They're releasing a positron, but also the calculations are much different here. They calculate the energy released. And we'll talk about that when we get to that one. And then we'll talk about gamma. Okay, almost done. It's one of the bigger, longer parts of this chapter. Usually would spread this out in multiple days, but that would be in class. So you just have to watch a bunch of videos at once if you want to. You could spread this out throughout the week. So what is the nuclear representation equation that represents the beta positive decay of tin? Remember, tin is Sn. It's tin 106. So I just got to find tin. Tin is 50. Tin is 50. Usually it's 119, so yeah, it's probably a radioactive version of tin. It's going to undergo beta positive decay. Okay. By doing so, the bottom number here, now you got to think about what happened in this, is that what is happening? So a proton changes into a neutron. So I lost a proton, it changes. It's just the opposite of beta negative. So what do we have? A proton. So this has got to be 49. So I've lost a proton, but it becomes a neutron. So my number on the top doesn't change. And 49 is indium, In. Okay, it's going to release a regular neutrino and gamma particle. There we go. Not too bad. Pretty easy. Just make sure the top numbers, the nucleons balance out, and the bottom numbers, the charge balances out. So when a proton changes in a neutron, a positron and a neutrino are emitted. So this, again, just like what we had before, a proton, which has a positive charge, so this is 1e, becomes that W boson, I think it's the W positive boson, and then it will decay and become these three particles. A neutron, which obviously has a charge of 0, a positron, which is a charge of +1, and then a neutrino, a regular neutrino, which is a charge of 0. So if I add all these together, I get 1e as well. So the charge just balances it out here. That's nice. So the decay of fluorine-19 should actually be, because this is wrong up here, fluorine-19 should actually be oxygen-19. It's a dotted particle, right? So I messed up. Comes oxygen. Oxygen is 8. Sorry. It's got to add up here. So this is +1 for this guy. And those two particles. So that's what I'm supposed to do. I'm supposed to add those two extra particles, which we did up here anyway. Okay. Nitrogen transmutes, which is the same thing as decaying. So nitrogen becomes carbon-13, nitrogen-13. So nitrogen is 7, and it's nitrogen-13, so it's 13. It becomes carbon, which is 6, and 13. So the top number didn't change. So whatever radiation had have 0 on the top. The bottom number changed. It went from 7 to 6, so the bottom number has to be positive. So this is definitely beta positive decay. It releases the regular neutrino and the gamma particle. Okay. Now the goal is to find how much energy is released in this situation. Now this one is a little bit trickier than the beta negative, because the beta negative, the electron that just popped into existence, just kind of worked itself into that ion and made an atom. They do separate, they fly off, but together they become an atom, if you would think about the mass-wise. This is slightly different. So let's see what we have to start off here. So we have 7 protons. We have 7 electrons. Okay, makes sense, that's an atom. Here, we have 6 protons, and we have 7 electrons. The electron count didn't change. Okay? And here we have 1 positron, not an electron, but a positron. Positron, I think. positron. No, I can spell this right. Positron. Okay, one positron, which is a positive 1. So if I look at the charge that I have over here, the charge works out, like balances out. This here is 1 negative because there's 1 extra electron. This is 1 positive, so everything balances out. All the charge balances out. But here I have 1 extra electron. So we have carbon, which is a 6 proton, 6, the carbon atom, so it's 6 protons, 6 electrons. Plus we have 1 extra electron, kind of just sitting there. So that's what's happening here. Right? And we have this 1 positron. Okay, so we have these extra pieces. In the previous one up here, we don't have the extra pieces. If I go back up here, this one, this calculation here, all of this together makes 90 electrons and, 91 electrons and 91 protons, which makes an atom. Right, so everything kind of balances itself out here. The electrons. Okay, so it makes an atom. But here, I have an atom and these 2 extra pieces. So these 2 extra pieces have to be accounted for in our mass because they're relatively small. Electrons are small. They're so small that we can't consider them or nucleons, but they do have a mass that could change our number depending on how precise we're being here. And we're being precise. We've got 6 decimal places here. So we're going to use those numbers. So I'm going to pull this sheet again, right? It has all my numbers. I have some of the numbers written here already. So nitrogen 13. Where's nitrogen 13? Oh, I don't have nitrogen 13 on this sheet here. Yeah, but here's nitrogen 16 and stuff. Oxygen 16, carbon. I have carbon 12 on here too. But I found these numbers. You can find them on Wikipedia. They're pretty well known. So the mass on the product side, or so the reactant side, I should say. Let's start off with the reactant side. Mass on the reactant side is my nitrogen, which is just the atom, 13.00573.9 atomic mass units. The mass on the product side is 13.003355 atomic mass units. That's the carbon, plus 2 masses of these guys, plus the mass of electron, plus the mass of a positron. Mass of a positron is the same as the mass of electron. You can look at the formula sheet. Sorry, it's all blurry, but it is on your formula sheet. It's right beside the electron. And the mass of electron is this number right here. So it's a really small number, times 10 to the negative 4, but it is there. So it's 2 times this 5.485799 times 10 to the negative 4 atomic mass units. Okay, so I'm just going to add those on and see what I get. 13.003355 plus 2 times 5.485799 times 10 to the negative 4. It's 2 of them because they are the same mass. Syntax error. What did I do wrong? Oh, an extra bracket when I shouldn't have. Okay. So my mass does change. It's 0.0445216 atomic mass units. But you notice it's still smaller. Products afterwards, it's 5.7 here. Now it's 4.4. So it does have a smaller mass. So there is a defect. There's a mass defect. So I'm going to subtract the 2 numbers. It doesn't really matter which way I go. Products minus reactants. I'm just worried about what the number is, not what the sign is. It is going down, though. 13.00. So I'm going to subtract the number. And I get 0.001286. There's a lot of decimals here. 286,402 atomic mass units. I'm going to change that to kilograms. Remember to do that. You times by that 1.66 number, times 10 to the negative 27 kilograms per atomic mass units. And I get 2.1361547 times 10 to the negative 30 kilograms. Okay, this is even larger than before. I'm going to change that into energy by using E is equal to mc squared. I'm not even bothering to write that in there. You're going to take my answer, times it by the speed of light squared, and I get 1.9225 times 10 to the negative 13 joules. And because we're in atomic physics, I'm going to divide by, or change it into electron volts. So I'm going to divide by that time, 1.6 number. Get 1.20 mega electron volts. I'm going to get this answer here. So here I'm dividing by the 1.6 number. What is this again? Electron volts per, or joules, sorry, per electron volts. I always forget those units for some reason. Okay. Now the number that we get is 1,201,578 electron volts. I'm going to just convert it into mega electron volts because that looks nicer. And there we go. Cool. So this is the tricky part, is that this is beta positive decay. We have this extra piece here. Right? We have actually two extra pieces. So we have to deal with that. And beta negative kind of just worked itself into an atom afterwards. So we didn't have to worry about it. Okay, so alpha decay kind of makes sense when you think about it. You're ejecting positive protons because there's too many protons. So if there's too many protons, they'll just push each other away and a piece will just fly out. It always just happens to be an alpha particle. Okay, it takes off two neutrons, two protons go with each other. That's a pretty stable part of it, and off it goes. The beta decay requires what we call the weak nuclear force. And it's weak because of how uncommon it is. Right? It's very unlikely it'll happen, so that's why they call it weak. It's not necessarily weak in the fact that Mr. Allen's weak or anything. It's just weak that doesn't happen that often. Okay, and it acts within the protons and the neutrons themselves. Okay. It's just, what you have to know about that later on is that the weak nuclear force is just responsible for beta decay. You don't have to know how it actually works. You just have to know it's responsible for it. So here's a beta chain. Thorium changes into protactinium. Protactinium changes into uranium. So this is what we call a decay chain. So I should be able to write this out. Yeah, we've got a couple of minutes here until I get the 15-minute mark. So thorium, 234. Thorium, remember, is 90. You keep it using a lot. You change it into protactinium. And protactinium is pH, which is 91. Okay. Now, what kind of decay is this? Well, it tells us it's an electron, but if I didn't tell you this, I should be able to determine it from here. Everything's got to add up on the bottom, so this has got to be -1. So this is going to be beta negative decay. Then that undergoes more decay, not the beta negative. The beta negative flies off and does its own thing. And the uranium, the protactinium becomes uranium. Uranium is 92. And again, through another beta negative decay. So this is a beta or a decay chain. You notice that they don't quite add up to the bottom. So the last one here doesn't add up to this middle one here, right? Or the first one doesn't add up to the last one. They don't have to in the beta chain, right? It's that the first and the second balance out, and then last balances out with that daughter particle here. The beta negative kind of flies off and does its own thing. So here, it's a bit tricky trying to think, okay, the numbers on the top and bottom don't actually add up. That's fine. They don't always have to. What's missing here, though, I should probably put the other pieces. Beta negative. So beta negative releases antineutrino and a gamma particle. And then this will turn into uranium-234, which is another beta negative. which is another antineutrino, which is another gamma particle. There you go. Cool. Gamma here, we just talked about this already. It just accompanies both beta and alpha decay. It's according to the Bohr model, photons are emitted when electrons move from higher energy shells to lower energy shells. So that's what's happening here. These excited atoms. So this protactinium is pretty excited because it changes shells. And when it restructures, it releases a gamma particle. It only releases one, which is kind of convenient. It's just high energy photon. Now, high energy photon means it has enough energy to ionize an atom, so it's considered as ionizing, which is like a X-ray and some ultraviolet. They are ionizing radiation. They are massless, they're moving at the speed of light, so they can penetrate pretty far. They can do a lot of damage. As long as when they hit something, they can go through a lot of stuff. They can go through like a meter of concrete before they get stopped. Okay. So this is the excitation that we were talking about before. This thorium is excited. When it becomes unexcited, it releases energy, and this energy is in the form of gamma. Gamma, I think up here it might say X-ray. It has the same properties as X-rays, but we call them gammas. There's a nice little video I'll put in the Google Classroom you should watch. Is radiation dangerous? And I'll talk about all the different types of radiation that you have. Some of it's dangerous, some of it's not. So we'll see that. And in the next video, we'll talk about radioactive decay series, and I'll see you then.